Our next speaker is Vasu Sharma. And Vasu is assistant professor and extension irrigation specialist at the University of Minnesota. Her research interests are in the areas of irrigation water management, water and nitrogen interactions, soil water dynamics, and cover crop work. So welcome.
Thank you. Good morning, everyone. I'm Vasu Sharma. As Bruce said, I'm in Soil, Water, and Climate Department at University of Minnesota. Been here since 2018, 2019 time and doing some research on irrigation management, nutrient management, focusing on nitrogen, nitrate leaching kind of work, which I'll be presenting with you today, and also some new work that we are doing in my lab on regional scale. So we'll be looking at that as well. All right, so this will be the outline of today's talk. I'll be talking, just setting up the stage. What is irrigation? I know most of you might not be irrigating, but talking about where irrigation is done, why it is done, what are the major issues that we are finding solutions to, and then talk about these 3 research projects, focusing mainly on the first one. I have 5 years of data to show you today. Talking about water response curves in sandy soil. So it will be similar to nitrogen response curve. Dan talked about them today morning. Similar to nitrogen response, we do these trials over years looking at where our optimum nitrogen rate is. So this research was focused on both irrigation and nitrogen to figure out where my optimum water rate is under these different nitrogen rates in sandy soils. So this is a 5 years data set that I'll be showing you, talking about irrigation, yield, evapotranspiration, and nitrate losses trends over time. Then we will move into some new studies that I'm focusing on, not so much data, but just giving you an idea of where we are going forward with these data sets. So starting with the introduction, why irrigation is important and where. So this map shows you the available water storage at 0 to 40 inches of soil profile in Minnesota. And if you look at the central sands region of the state, we do not have much available water storage. It's around 1 to 3 inches in 40 inches soil profile. Not all of the areas here are like these. There is a lot of rain-fed agriculture as well. Only 650,000 or around 700,000 acres of crop irrigation, which is, if you look at the total croplands in the state, around 3% of the total croplands. Not too much, but the water usage is very high, and I'll show you that graph. Mostly in these glacial outwash sands where we see these irrigation, so the red areas right here, and some in Dakota County area. Major crops that are grown in these areas, same as other parts of the state: corn, 48%, soybean, 20%, then some specialty crops like dry beans and potatoes, which are highly irrigated and need a lot of water and nitrogen to grow. Most of the water that we use for irrigation comes from groundwater resources. So 93% of the irrigation water that we apply to these acres come from groundwater. And what we are seeing from last few years, and this is the USDA census data, that there has been a 42% increase in irrigated acres from 2002 to 2022, which is a huge increase. And we will see that again in my next slide, where I show you the water trends. So what are the major issues? We are irrigating these sands, and we need irrigation to produce crop. In these sandy soils, there is no way, and I'll show you that data where we have rain-fed plots and we get almost no yield there. So we need to irrigate these soils, but at the same time, there are some issues that are associated with these. So this map here again shows you the similar thing that I showed in the previous slide, but looking at the estimated vertical travel time. So the sands where we have low water holding capacity soils, the sands, our vertical travel time is the water moves very quickly, so high, so hours to weeks, how the water moves. So if we are not managing these soils efficiently in terms of irrigation, rain is something that we cannot control, but irrigation is something that we can, right? So when we irrigate inefficiently, if we are over irrigating these soils, the nitrates or other nutrients that we apply, which are soluble, they can go very quickly to the groundwater resources. So there are issues with nitrate leaching, because all these systems are interconnected. When the water goes in, the groundwater is connected. These are shallow aquifers, so they are connected to streams nearby. And then also the wells, there is interference with that too. Another important issue that we are recently looking at is water quantity. So this is the trend of water use, billion of gallons, and then on the x-axis you see years and different sectors that are using these groundwater resources. The pink here is the purple or pink is the irrigation use. And I highlighted these drought years, and you can see even if you just point those drought years where we have these irrigation use is very high, it's also trending upwards. And this is also coincides with the increase in acreage in irrigation, because acres in irrigation is increasing, so the water use is also increasing. But you see these peaks in very dry years when we are using a lot of water, and not so much in years like 2024 when we got so much rain. So irrigation is very much driven by weather, but we see those very dry years in the mix where we are irrigating a lot, and that's where water quantity issue comes into play. And this is just a figure from the Department of Natural Resources website, where they have kind of assigned some groundwater management areas where we are seeing these decline in aquifer water issues, so related to irrigation management. So talking about the research that we are doing here at the U, this is kind of a snapshot of what we are focusing today and overall what my lab is doing. So optimizing irrigation and nitrogen use in Minnesota. We are looking at precision irrigation, variable rate irrigation. We are looking at no-till cover cropping, how we can include these conservation practices into the mix and look at how irrigation and these practices interact with each other, how we can improve our irrigation management, and then using some remote sensing and new technologies to answer some questions related to water quality and quantity. So first research project where I'll spend most of my time, I call it I by N study, but basically it is to gather some fundamental data that was missing in Minnesota to look at what is the optimum irrigation or water that my crop needs. So this is for corn over cone system, and that's our starting point. We are going into other crops as well with the similar kind of approach, but this study was answering three key questions. First is, how much water does the crop truly needs in these sandy soils, because these are vulnerable soils. What nitrogen rate best matches with that water level for maximum efficiency, and how can we use these relationships, the yield ET or ET, total water, how we can use these relationships to answer some questions that we are looking at. So our objective is to sustain high productivity for sure. We want to produce crop and we want to increase our productivity, but at the same time, we want to maximize our water use efficiency and also minimize pollution to groundwater. So this study was conducted at two research sites. One is at Sandplain Research Farm in Becker, other one at Westport, which is a Pope SWCD research site, and we have been partnering with them from a very long time. Both of the sites have sandy soils in general, but there are subtle differences. So at Rochelle site, our top 0 to 18 inches, where most of our crop roots will be, is sandy loam, whereas at Becker it's loamy sand. So a little bit higher water holding capacity at Westport with higher organic matter as well. But below our root depth, it's all coarse sand, so gravelly sand. So not too much difference, but when you look at the data, we have those subtle differences, and that also makes a difference when we irrigate these soils. This is our experimental design. We had 4 irrigation rates. So we started with 100% irrigation, and I'll explain what 100% irrigation is, because it's everybody interpreted in a different way. When I talk about these results, when I say 100%, that's what we use as 100%, not if farmer is using something as 100%. So just to clarify that. Then we reduce that rate 25% to make it 75%, then 50% and no irrigation. Those are 4 rates. And the nitrogen rates are from 0 to 350 pounds of nitrogen per acre in 70 pounds increment. What Dan explained today morning, we need at least some rates to create that response curve for nitrogen. Same word for the water. We need some some of those levels of irrigation, and that's why we have 4. If we would have 5 or 6, that would be better, but you all know it all depends on funding as well. We can't have like thousands of plots. So we stopped at 4 irrigation rates to create that response curve. So in total, we had 24 treatments that were replicated 4 times, so 96 plots at both locations, and we split applied, because it's sandy soils that's recommended. So we split applied nitrogen, urea into 2 splits, 1/3 nitrogen at V2 and 2/3 at V8, and then conducted this study for 5 years. I think I forgot to mention here, this study was funded by AFRAC. I have logos in the other slides, but I forgot to put it here. All right, so what is 100% irrigation? Just to make that clear. So we were monitoring evapotranspiration. We have different models that do that, and at the same time measuring soil moisture. So combining those 2 methodologies, we were making sure that our soil root zone, so stored water in the root depth here, always remains at 100% field capacity. There's a risk in doing that. The risk is that when the rain comes, we do not have enough room to store that rainwater, but that's the risk that we were taking. We wanted to see what happens when we do 100% irrigation and it rains. Is there more leaching losses or not? So our 100% is we are kind of matching the crop demand. So P minus ET, precipitation minus ET, is our irrigation. So whenever we maintain that water balance throughout the season and make sure that our water losses, which is runoff, and in sands, usually we do not have much runoff, but deep percolation or drainage losses are almost 0 or minimum when we are managing our irrigation. So in terms of measurements in this study, we had, as I said, 96 plots at each side. In first 3 replications at both sites, we were measuring soil moisture continuously. We were using this neutron moisture meter, which is one of the standardized method of measuring volumetric water content up to 4 feet of soil depth. So at 1 feet, 2 feet, 3 feet, and 4 feet. And then we had permanent suction cup lysimeters. And when I say permanent, it means that we installed them in the first year of the study and we never took them out, because there is a lot of variability that we have seen in the past. If we remove those lysimeters out, put them back, the data is very, variable. So this gives us confidence that our data, the first year data, we had a lot of variance, but in the next 4 years, we see that stabilizes a little. So we have 196 permanent suction cup lysimeters at both locations. Plant sampling, we do plant sampling at V8, R1, and R6 growth stages to understand nitrogen uptake. Then post-harvest soil samples, and then we also collect UAV remote sensing data. And I'm not going to talk about this objective of the study today, but I'll show you the rest of the data. So diving into the data, this is the nitrogen response curve. We have been talking about this since morning. The left side is Westport, the right side is Becker, and the 4 lines here are 4 irrigation rates. So x-axis is the nitrogen rate, nitrogen application that we applied. The y-axis is corn yield. And we see a very smooth nitrogen response curve that we expected at both locations. At Westport, we did not see a significant difference between the irrigation treatments. You see the 100% and 75% are kind of on top of each other, whereas we have a little bit less yield, under 50% at all rates of nitrogen, and way lower at rain-fed. So that's what I was saying. In sandy soils, if we are not irrigating, we are not going to produce a profitable yield. So that's what our data shows here, the blue line. The no difference, the reason for the no difference between 100% and 50% is that at Westport site, first of all, our soil water holding capacity was better than what we have at Becker, and also the rainfall frequency and the timing of the rainfall. So overall, the total seasonal rainfall wasn't that different, but when it rained, it also mattered. So at Westport, we got, even in the dry years, we got very timely rain, so our irrigation requirement wasn't that big at Westport as compared to Becker. At Becker, we did see significant differences between treatments, but not so much between 100 and 75%. Statistically speaking, 175% yields were not significantly different at both sites. Now you see other 3 dots here, or 4 black dots here. This is our economic optimum nitrogen rate that Dan talked about today. We looked at those and we wanted to see if our economic optimum nitrogen rate changes with irrigation. But on 5-year average data, we did not see a significant difference between irrigated treatments. There is a significant difference between rain-fed and irrigation, but not between irrigation treatments. And we have to investigate more. Why is that? Maybe analyzing each year separately and see the differences between wet years and dry years. But this is the 5-year average data, and we did not see a significant difference in EONR as well between irrigation treatment at both sites. At both sites, our EONR under irrigation was between 240 to 250 pounds of nitrogen per acre when we applied urea into 2 splits. Now, similar to our nitrogen response curve, this is our irrigation response curve. Okay, on x-axis now, it's the water in inches that we applied, depth of water, and on y-axis, it's corn yield. Westport and Becker, what we did, same as we do in nitrogen response curve, we calculated economic optimum irrigation. So I calculated net return, so dollars per acre, at corn, $5 per acre, and $10 per acre inch irrigation, and then try to figure out what is my optimum irrigation rate based on these data sets. And at both locations, we found that around 11 to 12 inches of irrigation, not total water, just irrigation is required. And this is just for one rate, which is closest to our EONR in this study, around 210 pounds of nitrogen per acre. It might change with different nitrogen rates that we have in this study. But now, is irrigation or water is the only driver for yield? Maybe not, right? So there are other factors like temperature, vapor pressure deficit that is driving your yield. So with irrigation management, our main focus is to fulfill the water demand or whatever the water requirement of the crop is. So the better estimation of that is evapotranspiration. So we want to, with irrigation, with supplemental irrigation, fulfill that ET demand of the crop. So what I did, I plotted total water, which is rainfall plus irrigation that's coming into the system, with the evapotranspiration, which is how much your crop is using that water. And we want to maximize that so that our yield is maximum. And what we found is that for Westport location, to meet that complete water demand of the crop, we need around 21 to 22 inches of water at 210 pounds of nitrogen application rate. And for Becker, it's around 22 to 23. So the range is between 21 to 23 for these central sands, which includes irrigation and rainfall. So let's say, yeah.
This is continuous corn and the plots are in the exact same spot every year, right?
Yes, this is continuous corn and plots are at exact same spot every year. That's true. Yeah, so our optimum range is between 21 to 23 inches of water. So let's say in years like dry years, when we get very less rain, our irrigation requirement will be higher. In years when we get a lot of water in rain, our irrigation requirement will be lower. But in general, on 5 years average, when we had those wet years, dry years, average year, this is what we found from the data. Other thing we looked at was nitrogen uptake. Was there any difference between irrigated treatments or rain-fed treatments? So this is for Becker site. On the left, you see stover nitrogen, grain nitrogen. This is both at harvest. What we found very interesting. First of all, no difference in between irrigation treatments. So 50, 7500 all had same nitrogen uptake. We got a very good response as expected from nitrogen. So these blue color. The red color is the rain-fed and the blue color is the irrigation, and the irrigation reduce as we go right. Good response with nitrogen from 0 to 350, but no difference here. What is interesting is at Becker, in stover nitrogen at harvest, we have significantly higher nitrogen under rain-fed, so when we do not irrigate. However, in grain nitrogen, we have lowest nitrogen in rain-fed. No significant difference between the irrigated treatments, which is very interesting how the water changes all of that, where the nitrogen is locating and how the plant is uptaking that nitrogen and where is putting that nitrogen, depending on the water input. But we did not see, again, at Westport, we did not see that. All of our treatments had same, significantly no difference, same nitrogen uptake at both in stover and grain. And this is essentially because the rainfall, how the precipitation was. So we got very timely rains at Westport. Even on our rain-fed plots got that water so that our nitrogen uptake was efficient. Now this is the nitrate leaching data. So we collected all of that water samples, sent them to lab, calculated nitrate concentration, then estimated drainage, multiplied with concentration, calculated load. So this is what you see after all that analysis. Leaching in this shows kilograms per hectare, but not a big difference from pounds per acre of nitrogen. And that's what we see. We see a decline in nitrate, not significant, no significant difference between 100 and 75, but still we see a subtle decline in nitrate leaching when we reduce that irrigation. We do not see a significant difference because mostly the leaching was derived by rainfall. So it's irrigation has an impact, but not that major impact as rainfall. Even not significant, we see 23% reduction in nitrate leaching under 75% irrigation when compared to 100% irrigation. At Westport, again, no significant difference, but if you just look at these first three, which is 100, 75, and 50, there's a slight decline in leaching when we reduce that irrigation rate. And very high leaching in rain-fed as compared to other because of the rainfall again, because at Westport we got those good rains that drive the leaching. So overall, our grain yield showed consistent curvilinear response. That's what we expected, and around 240 to 50 pounds of nitrogen per acre, we saw that plateau, and that's our for all irrigation treatments. That's our EONR. Our moderate irrigation, which is 75% irrigation, was not very significantly different in terms of yield and other things that we looked at, for example, nitrate uptake. So one recommendation from this project is that 75% could be something that we can think about when we are managing these soils, because we are not losing that yield. At the same time, we are saving around 3 inches of water overall on average, and then there's less leaching as well. On 5-year average basis, economic optimum nitrogen rate was kind of similar between these irrigated treatments, but lower in rain-fed, around 250 pounds, and then 21 to 23 inches of total water that is required to meet the crop water demand. And of course, nitrate leaching was reduced with reduction in irrigation. Quickly moving to our next topic, and I'll take questions at the end, but if you have any questions right now, I can maybe, yeah.
Maybe 21, 23 inches of rain, that's in the growing season.
Mm-hmm.
And that's just kind of perfect world. Adding irrigation when you're getting rain.
Yeah, so the question is this 21 to 23 inches of total water, which is irrigation plus precipitation recommendation. So this is starting from planting to harvest. So each year our planting and harvest dates were like plus minus 1 week, 2 week, but usually it's in early May to mid of October. That's what we are looking at, both precipitation total and irrigation total. All right, so now I talked about the problems that we have. How can precision irrigation, which is essentially variable rate irrigation, can address these problems of both water quality and quantity? So what is VRI? VRI is variable rate irrigation, and you all know that all fields are different, and within field variability exists, right? There are spots in the field where we have heavier soil. There are, even in the sandy region of the state, there are spots which are very sandy, needs more frequent, small amounts of irrigation, but other spots might not. So to address that problem, where we have this variability in the field, variable rate irrigation can be very efficient. So it fixes that problem and vary the irrigation depth across the field to match the soil water requirement. And why it matters? as you all know, if we are irrigating the soil where we do not want to irrigate, it's going to either leaching or the crop is going to be damaged. So it protects our crop, it protects sandy or elevated areas in the field, improves irrigation efficiency, it reduces energy use, also the nutrient leaching, and I'll show you that data. We have some of the data to support that, and also support more uniform crop development across the season. Now, something very important, variable rate irrigation do not work in all fields, okay? This is very important because the technology is there and everybody is excited to use it, but it's not useful for every field. Where it is not needed is fields with relatively uniform soils. So if you have pretty uniform soils, maybe you do not get that return on investment because this is very expensive technology as well. So if you have minimal elevation difference, your crop performance is consistent over years, you might not need VRI. This is one good example of a field where you might want to use a VRI. So very the elevation difference is very big. You got this ponding water here. You have very high spot here where you might have sandy soil. You might need to irrigate more frequently, smaller amounts. Now, VRI is of three kinds that's available in the market. One is speed control or sector control VRI, which means that it irrigates your field and it changes the speed of the pivot. When it is moving fast, it's applying less water. When it's moving slow, it's applying more water. So changing that speed of the pivot, you change the rate. So, but it only covers this pie shape variability, right? But mostly our variability is not pie-shaped. So if you want more precision, there is zone control VRI. So zone control VRI divides your field into different zones. So the small box is one zone where you can change your irrigation rate based on your field variability. And then there is more advanced sprinkler level. If you are looking into more precision or you have lots of variability in the field, or if you have variability in the soil and you are growing a specialty crop which has high value, this might be justifiable. So what it does is each individual sprinkler can be managed differently. So you can apply more precise water. Now VRI system is there, but how to create these management zones is the key. That's called prescription maps. And we have two kinds of prescription maps, okay? So this is example field. One is static prescription map, which takes into consideration your soil, your EC, which is your inherent property of the soil that doesn't change over time. So you use those layers and create these management zones at the beginning of the season and use these management zones for irrigating. So your one zone, for example, here the field is divided into high irrigation, medium, high, medium, and low irrigation, and you keep that during the growing season. But in dynamic prescription maps, which is a newer, or I would say still under research technology, so you change your prescription map over time. So you see the same field but different dates. We change that prescription map based on the remote sensing image. So we collect the remote sensing data, we create management zones every time we need to irrigate, and those zones change based on your crop growth. So those are more advanced or more time-consuming way of doing VRI. But what we are doing right now is doing research on this and see which one is better or which one gives us more, return on investment, I would say. So this is the same field. We divided this field into different pie-shaped plots and apply use static prescription map in one, use dynamic prescription map in other, and then the third one is uniform irrigation, no prescription map. So do not consider any variability. So we want to compare these three and see what the results are. I don't have results. This is the second year of the study. We have one more year, and then we will finalize this data. But this is in collaboration with growers in the state. So this is not small plot study. We have different growers in the central sands region who are collaborating with us. So we have production scale results for this study. Now this is another study that we conducted for 3 years at Stan Plain Research Farm, around 25-acre field. And we divided this field into different nitrogen and irrigation treatments. So irrigation treatments are essentially same. We use static VRI prescription map for variable rate, and uniform irrigation, only 2 treatments here. And we try to compare the results between these two. So this chunk of these 4 bars are uniform rate irrigation. On the right, you have variable rate irrigation under 4 nitrogen treatments. And I'm not going into depth about nitrogen treatments today to just respect time. On the y-axis, you have yield. What we are seeing overall is that with VRI, we have slight increase in yield, and that gives us a little bit confidence is that at least we are not decreasing our yield, okay? So we are saving a lot of water. The irrigation productivity or water use efficiency is very high, but at the same time, the yield is also very high under all of these nitrogen rates. The maximum is this one, which is 50%. So just to give you a context, this is the farmer's nitrogen practice, 50 split applications, 50% at pre-plant, at planting, and 50% side dress. With variable rate irrigation is where we found the maximum yield. Looking at the nitrate leaching, we also looked at, we had lysimeters in that field, and we collected under each treatment how the nitrate leaching differed. And that's what, again, is very promising is under VRI. So these two, the red and orange, is VRI treatment under different nitrogen. In both VRIs, we reduced nitrate leaching when we compare it with the uniform rate irrigation, which also tells us that variable rate irrigation is something that we can think of in these sandy soils or in the fields where you have a lot of variability. Okay, now moving into the remote sensing. Evapotranspiration is the crop water demand, and that's the most critical component in our soil water balance equation, because if we estimate evapotranspiration efficiently, I think the other things in the equation can be figured out. So this is something that we are focusing on right now. We have all the point data from our small plot studies from that big 5-year study. But that's point data, right? From Westport location and from Becker location, how we can use that data set and use some other resources like remote sensing and answer some regional scale problems. So we are estimating actual evapotranspiration or ET in central Minnesota irrigated croplands using these satellite-based products. One is Siebel, which is surface energy balance algorithms for land. It uses Landsat 8 and 9 images, and we process those and we kind of use surface energy balance rather than water balance and calculate the latent heat, which is evapotranspiration. And then the OpenET product, I don't know how many of you know about this. I'll show you one slide, but this is like ensemble satellite ET, again using kind of surface energy balance approaches, but many models together, and then give you a final product of what the crop evapotranspiration of your field is, using the same sources as Siebel. So this is when you log into OpenET, and it's free to use. You can create a login and go to the website. This is whole United States is covered now. And then you focus, it says draw custom area. You can focus on your field, and it gives you this very nice on monthly basis, on cumulative and daily basis evapotranspiration of how much crop water is being used. It's very useful for if you are interested in looking at in the season, what's your crop water use, but at the same time, we have now this data from last 6-7 years. So what we did is we used all of that data and created some maps for Minnesota that can be used by growers or by agencies to make some for decision making. So focusing on Siebel, this is just an example. We wanted to test this and see how what is our accuracy, and then validate our model first to go statewide. But we selected two watersheds. One is Clear Lake, other is Sauk. And this is the methodology. I'm not going into detail of that. So we collected all the Landsat images, cloud-free images, of course, did this methodology and calculated the evapotranspiration on monthly scale. So this is preliminary analysis for Sauk watershed. And this is the June, ET, July, August, and September. And these are all the acres, not just irrigated acres. But if you see, The resolution isn't that great, but if you see some of the acres are highlighted, those are the irrigated acres in the state. So this gives us a pretty good picture of, for planning purposes, how much crop water how much water my crop is using. This is for corn from last 5 years averaged. This is again the same thing for clear water. You can see this is a little bit southeast, and the ET has changed. We have a little bit more ET in clear water than at Sauk Center. What this tells me is that the irrigation requirement or the policy should be different for these different watersheds, or at least on some regional scale. We can't just use one number for every place. And we also validated, so our I by N study, so we had all that data from the study that I showed you earlier, Westport and Becker. That's our ground truth data. We had soil moisture data, we used water balance calculated ET, and we tried to validate for that location, so Siebel data with our water balance ET, and we found good relationship. The water balance ET also have some drawbacks, but I think this is something that which shows us that Siebel isn't that far. And we also compared it with Open ET, which is a validated product, and we are very close to Open ET results as well. Now this is the map that I was talking about, monthly and seasonal. I'm not showing you monthly, but this is seasonal corn ET, soybean ET at county scale. The highlighted counties are irrigated counties, and this is all acres, average, both rain-fed and irrigated. And I think these kinds of maps are very useful for growers, first of all, to kind of making some decisions on if they are digging a new well or putting a new irrigation system based on their crop, how much water requirement they should be having from that well, and also for policymakers. But then we were interested in only irrigated acres. These are so many graphs because this is on monthly scale. So May, June, July, August, September, and October. And we divided irrigated acres from rain-fed acres. Very interesting to see that I was expecting rain-fed acres having lower evapotranspiration than irrigated, but we found opposite. In the central sands region, rain-fed acres have more evapotranspiration than irrigated. The reason is because we are only irrigating sandy soils. The rain-fed acres are mostly on heavier soils. The irrigated acres are on sand. That's my reasoning. Okay, I don't know. We rechecked this data several times, and that's what we are looking at. In mostly May and June, when our crop is not fully, the canopy is not closed yet, the sandy soils are evaporating less because we have less water in there, whereas we have more water in our heavier soils, which are mostly rain-fed from the snow melt. Okay, so the sandy soils, they leach the water. I think the evaporation is lower than the heavier soil, which have more water holding capacity. So that shows that in the ET. But once the canopy is closed around July, August, and September, our ETs are almost equal between rain-fed and irrigated, and then at the end also. But you also see the scale is consistent at 150 millimeters, and you can see how the ET changes during the growing season. We have lower early in the season than when we have at reproductive and VT growth stages, we have higher ET, and then it reduces again at the end. We have similar graphs for soybean as well. Now, putting all of this together, right, we have so much data. How can we make use of this and give this to our end users who are our growers or people who are helping the growers? So we have decision tools, which is irrigation management assistant tool. We have been working on this since 2015. We have improved this tool so much, doing so much research on this, but there's still room for improvement. This is a working tool, so you can available for all counties. These were some initial counties, but now it is available on all counties of the state. You can go on this website, create an account, and create your field boundaries, and it will give you irrigation recommendation based on where you are, what your soils are. But moving on, our next step is to integrate all of this that we learned from these research projects. So this is the proposal that we submitted at various funding agencies. Hopefully we get funded. To idea is to improve the irrigation accuracy, of course, from our field research data that we will keep on conducting. But the second most important is how to integrate different tools that we have. For example, if grower is doing a variable rate irrigation, I talk to growers, and the most important thing they right now are focusing on is how to create the prescription maps. That's very hard, right? You need a lot of GIS or some geospatial knowledge to do that. What we are trying to do is integrating that tool with our irrigation management assistant tool so that growers just have to create a boundary of the field and we do the work for them. So we are doing the research on static dynamic prescription maps. So that work will go in this one. And then also collaborating with some private industry partners like Valley or the irrigation platforms that growers are using like Valley and Lindsay to also use their APIs in here so that the grower have one-stop shop so they don't have to juggle between multiple platforms. And then also validate and disseminate the extension work that we do. So this is my last slide, some takeaway messages. The first one is smart water nitrogen balance. We looked at those data sets. We figured out that same as nitrogen response, there is irrigation response, and our 75% irrigation is not too different from 100%. So there is just think about if you are managing these soils in years like very wet years, there is a possibility of reducing that irrigation below your field capacity as well, up to 75%. Then precision management technologies like VRI, they are very helpful in both improving water use efficiency as well as reducing nitrate leaching losses. Remote sensing products like OpenET and other products that are available are very useful for making these irrigation management decisions, and they are available also for growers' use. So, and we are also using them in our research. And then on-farm integration. So, if you're using some kind of tools like irrigation management assistant or any commercial tool, I think that's very helpful in understanding where my water is instead of just doing the guesswork, like today is the irrigation day, let's irrigate. So use some kind of tool like soil moisture sensors or some management tools to improve your management. And at the end, the collaborative impact. So I'm here today. You can ask me questions. You can shoot me an email. If you have any questions, I'm happy to collaborate on different research projects. And if you have any questions, I can answer those.
One more slide.
Oh, many questions. First one is, are there big differences in water use efficiency by corn hybrids? That's a great question. We did not look at corn hybrids in this project. At least all 4 years had same hybrid. But yes, the literature has shown that there are some differences in water use efficiency between corn hybrids as well, but we have not looked at those in our study here. The next one is the Westport data shows no difference in nitrate leaching and N leaching across treatments. You said there were timely rains. Were the timely rains for all 5 years of the study? No. So yeah, so that's another caveat for the presentation purposes. All of this data was 5-year average. We had wet years, we had dry years in this 5-year mix. So the trend was little different between those 5 years. And my next step is that's what we are looking at in terms of manuscript, where we are dividing these years into wet year scenario and dry year and looking at them separately. So yeah, for now, the timing, overall timing, yes, in all 5 years, it was better than Becker. Like Becker, we had like very dry spells, like 21, 22. There were like, I think, usually on average in June, July period, we get around 8 to 9 inches at Becker. We only got 3 inches at Becker in those years. At Westport, even the total amount was lower. Even in those dry years, we got very small rainfalls during the season. The next question is, how does irrigation affect rooting depth of corn? For example, does irrigation too early in the season tend to create shallow rooting depths? Yes, and I did not check that in this research, but yes, that's true from the literature that if we kind of put more water during the early stages of the corn, we stop that root growth. and then our root system do not develop and do not mine for that deeper water. So it's always recommended to use more deficit, or I would say management allowable deficit if you are managing irrigation. That's the term that we use. So higher MADs at the beginning or the end of the seasons, and then around 30, 40, 50% in the middle. Is the DNR adjusting seasonal water limits based on your data? That's a great question. Right now I don't know, but I am in conversation with DNR, some folks at DNR who are very interested now in talking to us and looking at these data sets and try to incorporate those into their policy making. But nothing concrete right now, just we started this conversation. Did you measure your lysimeters year-round or only in growing season? The values seem low. This is only the lysimeter data we start a little bit before planting because these are permanently installed. So we are not, we don't have to wait for planting. We start early, we end a little bit after harvest, but we only kind of do not manage the winter season because that's when everything is frozen. So there's no water in those pipes. But the data that I showed you is from planting to harvest. And also the value seems low because it's average of all 5 years. In dry years, we did not see any, in most of our lysimeters, no water at all because the crop was using that water very frequently.
Very good. Let's give her a hand. Thank you.